Hi everybody, I'm the greatest living inventor, and today we are doing my invention, p-adic entanglement. So let me write it down. P-adic entanglement. Okay, so I'm not sure you can see the marker. I will use a new one. Thank you. P-adic entanglement. Okay. So I'll take off my shirt. Okay. As you probably know, science today can't explain quantum entanglement. I invented an explanation to the hidden mechanism behind quantum entanglement. Okay, so I'm sure you know, you've heard of quantum entanglement. Quantum entanglement. Okay, so the problem, quantum entanglement, spooky action at a distance. Okay, this is a famous quote from Einstein. If we connect, entangle two small quantum particles in a special way, then after we connected them, we can separate them over very, very large distance, even two opposite sides of the universe, but still each of the particles will know what happens to the other one immediately, in spite of the fact that they cannot communicate between them. Such communication would take them years. Einstein hated it and called it spooky action at a distance. Okay, this is a quote by Einstein. Okay, so now the solution. This was the problem. Okay, the solution. My invention. Common action at a proximity. Common, like not spooky, action at, let's erase Einstein because I want it to be in the same line. Common action at proximity. Okay, so I'll explain in a moment. In a nutshell, "5 minutes 20", okay. In a nutshell, my theory takes the spookiness out of the particles and put it into the structure of space itself. First of all, please allow me to establish a few simple ideas that are unrelated to each other. Later, we will build on these ideas some more complicated ideas and tie them together. Okay, so metaphor 1, chessboard. Okay, so I'm raising. Metaphor 1, chessboard. Okay, the idea came to me from Richard Feynman's lecture on physics, lecture 2, basic physics, section 1, introduction. Okay, Richard Feynman. From lectures on physics, lecture 2, basic physics, section 1, introduction. In the game of chess, if a bishop starts on a light color squares, then it will be on the same light color squares throughout the chess game. Sorry. Okay, later. I had a sneeze, but I lost it. If it starts on dark squares, it will always be on dark squares. Okay, so the bishop, once you put it in some color, it stays on that color, either light or dark. Okay, metaphor 2, pixels. Let's put some more space between them. Metaphor 2, oh sorry, it's without the E, sorry. Metaphor 2, pixels. When I was a teenager, I liked to program graphics in DOS. Each tiny square of light on the screen is called a pixel. The screen resolution in DOS is very grainy, 320 pixels across and 200 pixels down. Okay, if this is the screen, so it's not in Windows, it's in DOS. So there are like squares on the screen, and each square is a pixel, and there are 320 pixels this way and 200 this way. Okay. Let's say we want to rotate a pixel of light, a point of light, sorry, pixel, around the center of the screen. Okay, we want, this is the center of the screen, we want to light one of the pixels and let it go like this or like this, never mind, to rotate something. We would hold the real accurate coordinates, in parentheses, floating point numbers with decimal precision in the memory of the computer all the time. Then we would do some calculations, sines, cosines, with these accurate floating point coordinates to figure out what is the next position of our rotating point, but not drawing anything yet. Now we translate round up or down the accurate floating point coordinates in the memory into not accurate at all integers, whole numbers coordinates, okay, without the points, the digits after the decimal point. So integers, whole numbers that are not accurate coordinates on the screen. Okay, this how did we call it? Grainy. Okay, so we have this on the screen. And we have another system on the in the memory which is accurate. Okay, like a memory of a lot of lines and a lot of scan lines. Okay, so, well, not scan lines, like rows. Okay, so the memory is much more accurate, and the screen is more grainy, it's not accurate. Okay, so if we have a pixel and we want to rotate it around, okay, around the center of the screen, then we light after this pixel and this pixel and this pixel and so on. But here we have a much more accuracy. We have in the memory we are calculating much more accurately, and then we round, we go to here and then we round, we lose the precision. Okay, like if it is 1.5 or like 1.5, then we make it 2. Okay, so it's less accurate. Okay, so now we translate round or down, round up or down, let's say round, the accurate floating point coordinates in the memory into not accurate at all integer, whole numbers coordinates on the screen, and we draw in the integer coordinates. Let's say this is the next spot, the next pixel. Okay, metaphor 3, distorting a mirror. Distorting mirror. Okay, so I'm sure you have seen this in a science museum or something, that you have a mirror that you stand in front and it makes you very tall and narrow, or very wide and short, these kind of mirrors. So metaphor 3, distorting mirror. You probably seen a distorting mirror in a carnival fair, mystery room, or in a science museum, optical illusions room. Let's think of a mirror that makes you look very tall and thin. Okay, so we have the person. This is our normal self, and then when we look in this mirror, we have something like this. If we hold the measuring tape or a ruler in front of that distorting mirror, we would see the number line compressed together. Okay, if we had a ruler in our hand, okay, we would see it here shortened, okay, squeezed. It would be the same height. My drawing isn't really great. It would be the same distance here, but much shorter here. Okay. If we would hold a measuring tape or a ruler in front of the distorting mirror, we would see the number line compressed together. We can think of another form of distorting mirror that is curved in its sides more than its middle. So it's distorting non-uniformly. The more you move to the sides, the more the numbers are close together. Okay, I cannot draw this, but think of Escher, the drawings of Escher, MC Escher. He has drawings that towards the ends are very, very small, and in the middle they are big. Okay, so now another headline, p-adic numbers and ultrametric space. Okay, so remember these metaphors and we'll use them in our head. Let's see, what time is it? 18, almost 19 minutes. I'm doing something. Sorry, p-adic numbers and ultrametric space. P-adic numbers and ultrametric space. P-adic. Okay. I'll try to explain what I'll try to explain here what p-adic numbers are. But do yourself a favor and read the friendly introduction in Wikipedia about p-adic number. Okay, p-adic numbers. In p-adic numbers, the closer you are, the farther you are. And the farther you are, the closer you are. Sorry. The world of p-adic numbers is upside down, in the sense that instead of the difference, we look at the reciprocal of the difference, 1 over the difference. Okay? So, p-adic numbers are upside down. Instead of the difference, we look at the reciprocal of the distance. We look at okay, instead of the difference, we look at reciprocal of the distance. Okay, so if the distance from two numbers, I'll give you examples, like so. Example 1. With normal numbers, 0.005 is close to 0.004. Okay, because the difference is 1 over 1,000. Okay, so this is close. Okay, this is in normal numbers. Normal numbers. And in okay, the distance is 1,000th. I can't say it, but 1 over 1,000. 1,000th. With p-adic numbers, the same thing is far. Why? Because we look at the reciprocal. So it's 1,000. Okay, it's not 1 over 1,000, it's 1 over this. So it's 1 over 1,000, which is 1,000. We flip it. Okay, this means flip. Reciprocal. Okay. So here in p-adic numbers, the same thing is the difference between them is far. This is far from this. Why? Because it's a distance of 1,000. The difference is 1,000. Okay. Example 2, with normal numbers, 5,000 is far from 4,000 because the difference is 1,000. Okay, we take another example. In normal numbers, 5,000 and 4,000 are far because the difference is 1,000. And in p-adic numbers, 5,000 and 4,000 are close because it's 1 over 1,000. Okay, close. This is close to each other in p-adic because we take the distance and we flip it. We make a reciprocal. Okay, and example 3, with normal numbers, 5 million is very far from 4 million because of the difference, which is 1 million. With p-adic numbers, 5 million is very close to 4 million because the difference is 1 over 1 million, a millionth. Okay? So 5 million and 4 million, the distance is normally million, but in p-adic numbers, 5 million and 4 million, the distance is 1 over 1 million, which is 1 millionth. Okay, it's hard for me to pronounce the TH. Okay, this isn't correct. Okay, what I'm explaining, it's not exactly correct, but it gives you the correct feeling of what p-adic numbers behave like. Also know that it's possible to do calculus and complex numbers and everything with p-adic numbers. Okay, so now you have the feeling of p-adic numbers. It's not exactly what I said, but this is how it feels like. It's pretty accurate for our purpose. Okay, and in real life it's totally accurate. It just behaves a little bit different. Okay, so now ultrametric space. We talked about this. Now we're talking about this. So ultrametric space, if you look up ultrametric space in Wikipedia, its formal definition is a space where every triangle is an isosceles triangle which is taller and thinner than an equilateral triangle with the same base. Meaning the base of every triangle is squeezed to be slim. Okay, so instead of an equilateral triangle, we have something more tall and slim. Okay? The base is squeezed. Sorry. It's the same height, but the base is, instead of like this, it's like this. Okay? So this is ultrametric space, it looks like this. Normal space, it looks like this. Ultrametric space, it looks like this. But that doesn't help very much. So a better definition from Stack Exchange question about visualizing balls in ultrametric spaces, and especially Mirko's answer there. Visualizing balls in ultrametric spaces. And especially Mirko's answer. Think of the Cantor set and its basic closed and open intervals. Note that for any such intervals, they either do not intersect or one is contained in the other. Okay, so the Cantor set is like taking the line and taking off, erasing the middle section. So it's like this, and after this it's like this. In each step we take off the middle, and after this it's like this, and after this it's like this. Okay, and so on. After this it becomes like dust. So this is the Cantor set. Okay, every person here is like a genius, but I don't have time to explain. I'm sorry. Now we are in 32 minutes and I didn't even reach the pictures. Okay. So, the reason I'm talking about the ultrametric space here is one, the p-adic numbers form a complete ultrametric space, and two, this fractal-like structure creates dust that is spread evenly and yet not continuously but discretely. Okay, it's like dust, but every particle of dust is by itself. Okay, so it's not continuous. The dust here, it's not a line, even though it will look eventually after a few steps like very close dots, but it's not a line. It's dust, separate particles of dust. So two, this fractal-like structure creates dust that is spread evenly and yet not continuously, but discretely throughout space. In parentheses, in the case of p-adic numbers, throughout the number line. Close parentheses. Another application, example of an ultrametric space is the tree of life in biology, also called Philogenetic Tree. Okay, so you have this is the root, and here are, let's say, animals, and here are plants, and here are fungi and microbes, and so on, like one-celled organism, multiple-celled organism, and the point is that here we have all kinds of animals and all kinds of plants, and so on, but the distance from this center and there are splits here, like the animals, the mammals are lions and us and so on, but all the animals, but the distance from the root to every end leaf, okay, the distance is the same for every leaf. Okay, and also you can see it here. If you see this like the root, okay, so it's like a tree, and this is like the end leaf. Okay, so also there is some, this is a binary tree, but you can see that it keeps the distance. Okay, here it's not the same distance to here, but all the end leaves are in the same distance from the root. Okay, and also here in this is the tree of life. I've seen even a picture of someone who made a tattoo of this. הלו? היי, אני באמצע הקלטה. אוקיי, תודה, ביי. Okay, sorry, my parents. So this is the tree of life. And this is, we said, the Cantor set. This is an example of ultrametric space. Okay, so the distance from the root to the end of every leaf is the same. The Cantor set middle point are also shown like a binary tree in red color with this property in one of the pictures in Wikipedia under a Cantor set. Okay, now a discrete space. Okay, let's make a title. I'm erasing everything. Discrete space. Okay, so now after a long and hopefully gradual preparation, we are getting to my theory. My first step is that I think space is not continuous, but instead space is discrete. This idea, this isn't as bizarre as it sounds. You can read it in Wikipedia Quantum Space-Time. So it's one word, quantum space-time. In Wikipedia, quantum space-time. Okay, one set of rounded coordinates. I think that the space that we see is like the pixels on the screen metaphor. Of course, instead of 2D pixels, Mother Nature uses 3D voxels, and she has better hardware than a personal computer. The display coordinates are the only type of coordinates that we can see. They are like the integer values of the little squares. The real calculations of movement, before being rounded for the display squares, are done in two other systems of coordinates which are a lot more accurate. Okay, remember, like the screen not accurate and the memory accurate in the computer. So now two sets of accurate coordinates. Okay, this is not accurate. This is, yes, accurate. Two sets of accurate coordinates. And this exists together, like in the computer. There is the screen, what we see, and there is the memory, what we don't see, but what is working behind the scenes. They exist together. This is real and this is real. But we see only this, the screen. Two sets of accurate coordinates. Most people know about the rational numbers, something divided by something else. But what most people are unaware of is that these numbers come in two flavors, normal and p-adic. Okay, you know what p-adic is. But we know that p-adic numbers are just as good. And they also have their special property of flipped distance. Remember, reciprocal. So I claim that normally all the particles are on the normal rational coordinates. But when we entangle two particles, what we are actually doing is giving them a little nudge and push them onto p-adic coordinates. So to us, they look the same because we only see the rounded display coordinates. Okay, rounded. And the two accurate coordinates are doing rounding in the same way. But in fact, the two entangled particles are close to each other because in p-adic world, the further apart they are, the closer they get. Okay, so in the opposite sides of the universe is actually very, very, very close, for example. Okay, now, distorted mirror interpretation. If the p-adic distance behavior still makes no sense, think about the following model. In every normal coordinate on the number line, we put a normal glass window, so what is near looks near. What is far looks far. In every p-adic coordinate on the number line, we put distorted glass window. So what is near looks far, and what is far looks near. Remember, it shrinks the number line horizontally so that even the opposite ends of the universe become near. Okay? So initially I got it wrong in my book, so now I read it correctly. Okay. The next one, distorted chessboard interpretation. Okay, distorted chessboard interpretation. Let's say that the light color squares are the normal rational coordinates. The dark color squares are the p-adic coordinates. Okay, I don't have p-adic anymore, but you remember what p-adic means. This flipped coordinates. What is near is far, and what is far is near. Once the two bishops were pushed slightly to the dark squares, the other pieces are transparent for them. The two bishops have a clear line of sight to act on each other. What's more, the special structure of the p-adic space means that while the light color normal coordinates grid remains rigid and flat, the dark color p-adic coordinates are curved, so that very far away ends become close together. This is like the situation on a ball. On the ball we live in, planet Earth. When you walk a long distance from where you were, far, you eventually return to the same place, close. Okay, visualization with wooden chessboard. Okay, so this chessboard is very dear to me. I'll show it to you. Okay, it's this chessboard. This chessboard is very dear to me. It was handmade by my father when he was a boy. On the other side, it closes like a box for the pieces and also has backgammon triangles inside. Okay, now, one, how it looks to us. Okay, so I'm showing you the picture. This is how it looks to us. This is reality the way we see it. Okay, you see that all the pieces are close to each other. This is continuous. But in reality, in actual fact, it's not continuous. It just looks like that to us. So number 2 is discrete space. So I will show you discrete space. Okay, so this is the way it more accurately is. They are spaced and there is a discrete gaps between them. Their locations are discrete. It's not continuous. They cannot be wherever they want. They can be only in these slots inside reality. 3. Entangled bishops colored in black. Okay, so here we have two bishops, and one of them started on the white, but then we moved it to the black, and now it's to the dark side, the dark squares, and now they are both on the dark squares, and now they are entangled. Okay, so they have a clear line of sight to each other. Okay, the next picture, number 4, curved space. Okay, this is curved space. You see they are even closer because the space is curved, these two bishops. And number 5, last picture, entangled bishops on ball. Okay, so if we apply the p-adic world, then they are very close even though they are very far. Okay, so they are actually very close, like on a ball, like you go around the earth and you come to the same place. Okay, so this is a soccer ball, but it was useful for my explanation. Okay, so proper disclosure. After I thought about this myself, I found a physicist named Tim Palmer who have a similar theory. I'll write his name. Tim Palmer. Okay, so after I thought about this myself, I found a physicist named Tim Palmer who have a similar theory. At least I think it's similar because I cannot understand the hardcore mathematics. A link to the non-technical article in the magazine New Scientist, so I'm giving you the link in the video description. New Scientist, blah blah blah, can fractals make sense of the quantum world? A link to the full article here. Thank you, Stealth Skater. And you can read about Tim Palmer in Wikipedia. He's very impressive. He started from, he's an expert in climate, okay, in weather. So, and also about his theory, invariant set postulate. Invariant set postulates. And also this technical article by Tim Palmer that really sounds like what I'm saying, at least the headline, and the rest I cannot understand. P-adic distance, finite precision, and emergent superdeterminism, a number theoretic consistent histories, approach to local quantum realism. And see also P-adic quantum mechanics. Okay, also in Wikipedia. So, but I'm not sure it's the same what they're saying because again, I cannot read the mathematics. So thank you very much. This was my invention. I hope it was clear, and I'll see you in my next invention. So thank you very much. Thank you.